This example comes out of section 8.3, Laws of Logs, and we're talking about the pH scale. Now, different Math 30 students have different backgrounds with talking about acids and bases, but even in Science 9 and 10, you run into the pH scale a little bit. pH stands for power of hydrogen. It's basically a measure of how acidic something is. The more acidic it is, the lower it is on the scale. So something like battery acid, for example, is a very, very strong acid, and it is way down low on the scale, like in the 0 to 1 kind of range. A weaker acid would be something like vinegar, a little bit further up on the scale. Things are compared to distilled water, which is considered neutral, right in the middle of the scale at a 7. Something that's a little bit basic would be something like baking soda. So baking soda would be up here. Really strong bases can be actually just about as dangerous as really strong acids. Something like lye or very strong detergents and soaps sometimes are very basic. Most things that you eat wouldn't be very basic because bases are quite bitter, whereas acids are quite sour, which is something we can seem to handle a bit better. You will be given an equation for pH. It's negative log the concentration of hydrogen ions in your solution. So our first question is this. We're asked how many times as acidic is cola compared to milk, and we're told that the cola pH is 2.5, quite acidic. Actually, it's got the same acid in it apparently that removes rust in rust removers, compared to milk's pH, which is 6.6. And so if I set this up and figure out how much hydrogen cola has in it, 2.5 equals negative log the concentration in the cola. And so 10 to the negative 2.5 is the concentration of hydrogen ions in cola. Now, for milk, if I won't go about the same steps, I'm going to find that 10 to the negative 6.6 is the concentration of hydrogen ions in the milk. So if we're comparing the acidity of these two solutions, we've got 10 to the negative 2.5 in the cola, 10 to the negative 6.6 in the milk. Find that that's 10 to the 4.1 times as strong. If you calculate that, it's about 12,589 times as acidic. Every step on the pH scale is a factor of 10. So if you have an acid that's a pH of 1 compared to an acid that's a pH of 2, the 1 is 10 times as strong. So in this case, we're 10 to the 4.1 times as strong. Now the second question says an apple is 5 times as acidic as a pear. So an apple is 5 times. And we're given the pH of the pear. The pear is a pH of 3.8, so we're asked to find the pH of the apple. Now, we can find the concentration of hydrogen in this pH of 3.8. So the pear has a concentration of hydrogen of 10 to the negative 3.8. H plus for the pear is 10 to the negative 3.8. We know that the hydrogen in the apple must be 5 times as much. So it's just going to be 5 times 10 to the negative 3.8 without doing any fancy calculation. So if we just take the pH of that, negative log of 5 times 10 to the negative 3.8, and crunch those numbers, you get that this apple has a pH of 3.1. Again, if you remember that every one tick on the pH scale is actually a factor of 10, it makes sense that these two fruits here must not be a whole tick apart on the scale. That, the fact that they're 0.7 units apart on the scale indicates that they are less than 10 times, it's not quite 10 times as acidic. So pH scale, decibel scale, Richter scale, all different examples of logarithmic applications that you could run into at any time.